It has to start now. Okay, so what I would like to do, first of all, as always, is to start with the problem of the day. The problem of the day had a bunch of big O exercises. And to make sure that we work with this, let's go through with these. It's basically a bunch of relations. Is this true or not? So when we say, is 2 to the 2n squared plus 1 big O of n squared, how would we decide that? The answer is we go back to the definition. Okay? If we're confused, is there some constant c times n squared such that this is bigger than or equal to 2n squared plus 1? The answer should be clearly yes, right? For n equals 3 or so. It's eventually going to get big enough, right? Anything bigger than 2. So the answer here is true. Is square root n equal to big O of log n? Okay. How would we answer this one? Well, you ask yourself, is there a constant times log n such that that's bigger or equal to square root n? That maybe doesn't help you as much this time, right? Because you need to know the relationship between square root n and log n. Last class I talked about the dominance, right? And I said that log n is dominated by any polynomial. Okay? You could prove that with limits, but I find it easier to accept it. Okay? Once I accept that, the answer here is really no, because this is n to the 0.5. This is log n. Okay? Any questions about that? One other way that may make it easier for you to see this, by the way, let me show you another way to write n. Can anyone think of another way to write n in terms of logarithms? Logarithm, n is equal to 2 to the log n. Does everybody believe that? Log base 2 of n? Isn't that true by definition? How many people look at that? How many people see this and say, oh yeah? How many people say, I don't see what you just did? Who here says, oh yeah? Who here says, I don't see what you just did? No one. So I'm seeing one oh yeah and the rest no one. Okay, so I'm going to have to say, the majority of people say, oh yeah. Okay? So if so, what does this mean? Another way to think about this is that this is comparing the square root of 2 to the log n versus log n. Certainly something raised to the exponent of that looks like it should beat up on it, right? Everybody agree with that? So if so, the answer to here has got to be false. Okay? Any questions? The question here is the other way. Is log n in big O of square root of n? Well, the answer is this grows much faster than that, so the answer is true. Any questions how I would reason about that? Next one, I've got this thing, n plus 1, n squared plus 1 square root n times that versus n squared log n. What would I do with this? Well, the first thing I would note is n squared times 1 plus square root n. I might as well get rid of that 1 plus square root n is big O-y is the same as square root n. Does everybody see that? Here I've now got n squared log n versus n squared square root n times n squared log n. If I want, I guess I could cancel the n squareds. This might be how I would think about it. And now I'm back to the same comparison that I had before, right? So the answer here has to be false. N squared square root is much bigger than n squared log n. Any questions about that? People see why that is. Well, the left side, before I made it messy, I can even try to erase it. This was n squared times blunk 1 plus square root n. Right? Is that what it sees? N squared times 1 plus square root n. Okay? So another way is it's totally n squared plus n times square root n. It's clearly n squared plus is unimportant, right? So the heart of the matter is the n squared square root n versus the n squared log n. And if we're thinking about, is it in there, again, I would think about, dividing, canceling common terms, and you reduce it to something it's a no-brainer. Any questions? Next one, 3n squared plus square root n. How does that compare to n squared? Is it in big O of this? Well, this plus this dominates, the 3n squared dominates the square root n, right? Might as well get rid of that. 3 times n squared. How does that compare? I don't care about the 3. So now you're asking me n squared, is it in O of n squared? No brainer. That one's got to be true, right? Square root of n log n. How does that compare to n? Okay? Which is another way to think about this. Again, this is n to the 1/2 log n. This is n to the 1. Which exponent is bigger? This one. Another way to write this thing, what's another way to write n to the 1? You could also write it as square root n times square root n. Isn't that true? Now then, square root n and square root n. Now what do we have left? A log n on this side and a square root n on that side, right? It's clear that this is bigger than that. Okay, and so the answer to that is true. Any questions about that? Here is something funny on the last one. It says n to the 1 over minus square 1/2. What was that? That, I think, means 1 over the square root n, isn't it? What happens to 1 over square root n as n gets bigger and bigger? Does everybody agree it gets smaller and smaller, eventually going down to 0? So the plot of this thing is looking like that, something like that. So is log n, this thing, if we take a look at it, this thing is basically going to 0. Is log n always less than or equal to something that's going to 0? The answer is no, right? So the answer here would be false. Any questions about that? A good question would be, I don't understand that one. Any questions? Okay, are these sort of clear? Questions? No questions. Okay? So once you start to work with this, this is easy. The big O problem is the one that's supposed to be a gift on the midterm. Okay? Because once you work it out, it's mechanical. You don't have to think about this one. You go back to the definition, or you just remember the relationship between the component functions we know about. Any questions? Okay, good. Bunk, bunk, bunk. Okay, so we're talking about logs, and I just wanted to spend a few minutes concluding with 1 or 2 very important facts about logarithms. We saw logarithms last class. The important thing is that the log of n is how many times you have n until you get down to 1. That's how I think about logs. Or it's the number of times you double 1 until you get to n. That's how I think about logs. Okay? Now, there is this notion that for any logarithm, there is a base to that logarithm. So log base c of x, what does that come in? Basically, for any value c, any sort of constant c to the log base c of x is equal to x. That's the definition of the logarithm function. Now, normally when I think about logarithms, if I'm talking about doublings or halvings, I'm thinking about log base 2. The interesting thing is that in general, the reason why I get away thinking about 2 is that big O-wise, the base of the log doesn't matter. And the reason it doesn't matter goes back to this expression that you saw in high school that gave you a way to convert the base of the log. Everybody agree they saw logarithms in high school or some other pre-college math. I don't know where you saw it. Somewhere you saw this thing. And what you saw was that the log of b base a is the log of c base a divided by the log of c base b. How many people remember seeing this expression? Okay, so this shouldn't be mystery. How many people have never seen this before? No one will say they didn't see it before, but you probably just don't remember it. But what was useful about it, what was this useful for? Suppose I have a log written in base c, a base c logarithm, base 10, base e, base 2, base 100. And I want to convert it to some other base, 1.7. How would I go about doing it? It says that the log base a of b is equal to the log base c of a, the log base b of a is the log base c of a, okay, divided by the log base c of b. So what is interesting? Suppose we read and write a and call it n, okay? And we think about the log base b as being base 2, and the log base c as being, let's say, base 100. B and c are constants. N is n, right? What is the log base, in this case 100, of 2? How would you find out what the log base 100 of 2 is? You punch that in a calculator, isn't it? Everybody agree your calculator has the power to figure out what the log base 100 of 2 is? Anybody doubt that? Well, what is the log base 100 of 2? It is a number, isn't it? Everybody agree with, everyone will agree with that. That's a number. It might be, I don't know what it is. Okay, I guess it says so over here. It's 1 over 6.6542. It doesn't matter to me what that number is, but it is a constant. Does everybody agree with it? That for any fixed base b and fixed base c, to convert a log base n, a log of n, from one base to the other, I am just multiplying it by 1 over this thing. That is a constant, right? What do we say when we have a function, log base b of n? And we can say that that is equal to some constant times log base a of n. What does that mean to us? Big theta-wise, these two functions have to be the same. Does everybody agree with that? Think about this for a second. This is important. This is power. All right? It means that big O-wise, binary search divided it by 2's. Okay? What's your lucky number? You have a favorite number? 8. What's your name? What? Anuj. Let's now talk about Anuj search. What is Anuj search? You divide the thing into 8 pieces. Okay? And now look to figure out which one of the 8 ones it is in. Okay? Is Anuj search going to be logarithmic? Binary search will be divided into 2 pieces. Anuj search is going to divide it into 8 pieces and look in the right one. Is that going to be order log n also? Certainly it's going to be log n. Okay? What about Skiena search, which is going to divide it not into pieces of size 8, but let's say one piece of size 2/3 and one piece of 1/3. So it's a lopsided binary search, right? I don't always find the middle. I pull off 1/3 of it. Does everybody agree that somehow that in this case I'm dividing it in the worst case, not by a half, but by 3 halves? Okay, I'm getting someplace where the size is good. In the worst case, it's not going to be as good as if I divided it equally, right? People see that? Binary search in the worst case works well because both sides are balanced. If one side was bigger than the other, in the worst case, it would always fall in the bigger one, and it would take more rounds to terminate. Do people see that if you're unlucky? That if I was doing a search, and maybe this is getting a little too abstract. Suppose I divided, instead of looking at the middle element, median element, I looked at the one in the third position. After one round, I have 2/3 of n elements left to look at, right? After 2 rounds, I have 2/3 squared n elements to look at. Right? Does everybody agree with that? How many rounds will it take for my lopsided binary search to end? Okay, it's not binary now. It's sort of this 1/3, 2/3 thing. If I'm always unlucky and it gets on the 2/3 side, how many rounds will it take? Well, you say log base 3/2. I can't do that so fast, but I can tell you it's 2/3 to the h times n. I want to know how many times do I take 2/3 of this until n gets down to 1. Does everybody agree that's the answer? If each time I take, I am stuck with 2/3 of it. Okay? So what is that going to be? Well, multiplying both sides by 2/3 to the h. This is equivalent to saying n is equal to 3/2 to the h. Does everybody agree with that? And if we agree with that, if we take the log of both sides, log base 3/2 of n is equal to h. Okay? Is this thing going to be big O the same as log base 2 of n? The answer may be bigger, but it's big O. It's constant. It's asymptotically the same thing as binary search. That's what the argument here is saying. The log of the base doesn't matter. So long as it is a constant, it doesn't matter really what constant it is. And big O-wise, the log function does the same. Any questions about that? See some blank faces, so a question might not be bad. Okay? Question? Any questions? Okay. So what's interesting is that the base doesn't really matter. One other question here. Big O-wise. Suppose I take the log of n squared. What is the log of n squared? Does anyone know? Okay. That's the equivalent of 2 log n. Why is that from other stuff we have seen? You know, basically the rule is basically you drop the exponent down and you multiply it by the log of what's left. Why is that? What is the log of n times n? That we saw last time, right? What is the log of n times n? What's log n plus log n? 2 log n. Does everybody now believe that? Right? What is the log of n to the 100? What is the log of n to the 100? 100 log n, right? Notice that the log of n to the 100 is asymptotically the same as the log of n. You see that? The log of any power, and log of n to the 100, is in big O of log n. Right? Because logarithms are so powerful, they can chop up any polynomial. Okay? N to the 100, n to the million. And big O-wise, it doesn't make any difference. Okay? Any questions about that? Any questions about that power or property of logarithm? Or anything else about logarithms? Okay? It's important to feel where the logs come from. There's this algebraic manipulation that we're doing with logarithms. And that's important, good to be able to do. But the important thing is to feel to feel in your bones when you have a logarithm, okay, and know how to recognize it. Any questions? So towards that end, I would like to give you one last example of logarithms in action. Okay, I was once visiting a friend of mine who was a lawyer, and I was waiting for him to do something. And there was the federal sentencing guidelines were on his desk. What are the federal sentencing guidelines? Suppose you commit a crime. how do they know how many years punishment you deserve for this crime? The answer is, to a certain extent, they've reduced this to an algorithm. That's the federal sentencing guidelines. And that they will say, let's see, you knocked off a liquor store and stole $7,000. How much time should you serve for this? And in those federal sentencing guidelines under fraud is a table like this, okay, which says that if you steal this much money, more than $2,000 but less than $5,000, you add 1 to your punishment level. Okay? If you steal more than $120,000 but less than $200,000, you add 7 to your punishment level. Okay? What is interesting about this particular crime, this particular table in the federal sentencing guidelines? Can anyone look at this and see something that looks interesting? Well, it's exponential, but what is exponential is the question. The amounts are growing exponentially. Why is that? They are doubling. 2 times 2 is 5. Well, it's close enough. 2 times 5, again, big O-wise, I don't worry about things like this. 2 times 5 is 10. 10 is 20. 20 is 40. 40 times 2 is 70. 70 times 2 is 160. Does everybody see that in a big O sense? Every one of these things is essentially doubling, right? So in this side, the amount of money in the table is growing exponentially. Does everybody see that? How is the punishment, the increase in punishment level, growing? Linearly. What does this suggest? What? Okay? It says that your punishment is growing very slowly in the amount of money that you're stealing, right? We do a graph where here was punishment, and here is dollars that you steal. You get a curve that looks something like that. Does everybody agree with that? So here's a question for you. You say, I want to steal $1 million, okay? I have a choice of doing one crime to steal $1 million, or knocking off 10 liquor stores at $100,000 each. Which will get you more crime, more punishment? That would be 10 times this. Where was that? That would be 10 times this. Let's say it was 10 and 100,000. That would be 10 times this level would be 30, versus 1 times this level is 7. Does everybody see that the moral of the federal sentencing guidelines is if you're going to steal money, steal it in large quantities, okay? The key thing that the federal sentencing guidelines are trying to teach us, okay, is what? Okay, basically, if you do the crime, make it worth the time, okay? Any questions about that? So if you got any vocational advice from this class, that would be the vocational advice that I will give you, okay? Any questions about it? The serious point from this is to recognize when you see something growing logarithmically, okay? Because that means that it is growing slowly, okay? And that is sort of, if you interpret that right, that is important information to know, okay? We like things algorithmically where the running time grows logarithmically because that is very, very slow. Any questions? Okay, any questions about logs one way or another? Okay. So what I would like to now start to talk about is basically elementary data structures. Data structures are what I would like to think of as the building blocks of more sophisticated algorithms. Everyone here took what I call a data structures course. You might call it CSE 214, is that right? Okay. And in there, did you guys do binary trees? Everybody who did binary trees, raise your hand. Everybody who did not do binary trees, raise your hand. Okay, everybody says they did binary trees. There's a lot of, in a course like that, you learned about basic data structures, okay? And you learned, and I'd like to spend the next class or two basically reviewing the material that you learned in data structures. Because data structures are sort of the building blocks that we're going to build more sophisticated algorithms from. One quote I always liked was this quote that said that man's progress is measured by the number of things we can do without thinking. And so as a computer scientist, as you march up this level of algorithmic complexity, the fact that if you can think in terms of priority queues, stacks and heaps, and think about binary trees and balanced binary trees and hash tables, you are thinking at a higher level automatically than if you start talking to me about lists or arrays. There's a certain level of abstraction that comes from thinking about these structures at a higher order. And so I want to review the basic data structures and think a little bit more about some of the issues that come up in data structures. Because one thing that I've noticed, again, I wasn't there when you were taking your data structures class. Over the years, the role of a data structures class has changed somewhat. Again, in the olden days, when I went to studied computer science, that was before object-oriented programming. And you sort of grew up thinking in terms of operations and algorithmic efficiency quite a bit, okay, just because it was the nature of what you were doing with these things. You guys grow up supposedly in an object-oriented world. Many of you times when you say you want a data structure, you don't think about rolling your own. You guys, is there some kind of a stack class? You guys, is there some built-in stack class you guys know about? Yeah, so you guys say, I'm never going to write a stack. I'll use some library, right? And this is a good thing in general. The thing to recognize that I want you to be aware of, because it causes a little bit of a disconnect from how you're thinking about it, is that when we deal with data structures in here, there are two different dimensions to thinking about them. One is the abstract operations that they support, okay, and the idea of viewing them as black boxes. The other thing that we're actually going to be, in some sense, more concerned than what you're usually concerned with is, what is the implementation of these operations? For many of the basic data types, like let's say priority queues, let's say dictionaries, these are the important ones. There are many different implementations that you can use under the hood to make a dictionary. And realizing what the trade-offs are between one implementation and another makes a big difference. If we're using a dictionary data structure, let's say a tree or a sorted array or something like that, as our underlying representation of a dictionary, then it makes a difference when we use that dictionary in an algorithm. The running time of the algorithm is going to depend upon which implementation we use. Okay? So it's important to be able to think about the underlying operations, the implementation. And that's what we're going to sort of focus on today a little bit. Any questions about what data structures are, why we think they are good things, anything? Okay. So again, the idea of data abstraction, which is what I gather they've been teaching you in now that you are object-oriented programming people, is to think about a data structure in terms of the operations it can do. If you have a stack data structure, what are the operations a stack can do? Push, that means stick something in the stack. Pop, take something off the stack. Is that the only operations you have in your stack class? What? What is peek? Peek means tell me what's on the top of the stack, but don't remove it, right? Any other operations on your stack class? Probably initialize the thing, right? Initialize the stack so that you can start to put something in there. Maybe you'll want to ask how many elements are in your stack class, right? In your stack. So there are a lot of operations that somehow abstractly describe what your stack is. And in principle, if you write your program in terms of these abstract operations, for correctness purposes, it doesn't matter if you use a linked list or an array or whatever as your implementation. So long as the implementation is correct, your program will be correct. But we're dealing with efficiency in here. And so different implementations have different efficiency issues that we're going to worry about. Okay? Any questions? So when it comes to data structures, what I consider to be the big divide in data structure implementations is between contiguous allocated structures. Things like arrays, matrices, hash tables, okay, and linked structures. Things like lists, trees, okay, linked lists, things like that. And it's important to understand really what the stakes are in the two differences here, okay? What is an advantage? Let's just, you know, I have it on slides. Let's take a look at this thing. What do people think are the advantages of arrays over linked lists? Everyone says, yeah, I used an array when I was 6, and I didn't like linked lists, or something like that. It involved pointers. It's tricky. Why do people like arrays? What is a good thing about an array? So the good thing is that in an array, access of if you know the index of an element, you can access it in constant time. Does everybody agree? Correct? What else is good about it? Again, the analogy that I like to make is somehow, I think of an array as you have a house, a street of houses, right? And you know, the index is like the address of the house, right? And if you know the length of the street and how wide the houses are, if you want to know where is this house, given the address of the house, it's easy to find where it is, right? Supposedly in Japan, they allocate house numbers on a street in according to the order that the house was built. So if you have a street like this, I always like this example. I'm not completely sure it's true, but it's a great example. Where, you know, supposedly when you're building a street in Japan, oh, here's the first house, I'll name it 1. Second house, I'll name it 2. Third house, 3, 4, 5. What is good about this? Okay, if you're building houses, streets in Japan, you need to know what number to give your house, right? You don't need to give any surveying of the street or anything like that. What is the bad thing about this? You want to try to find where somebody's house is. It's impossible, right? I live in, you know, let's say, imagine in Manhattan, we labeled Broadway like this. I live on 716 Broadway. Okay, well, where is it? Well, it's, you know, it's the house labeled 716. Okay, you would never find it, right? The fact that we have an index lets us find things quickly. Okay, and that's a good thing about arrays. What else is a good thing about arrays? Yes? So from space efficiency is a good thing about arrays. Why? Because when we compare it to linked structures are, you know, in 10 sense you have a data field and a pointer field, typically in a linked structure, right? That means a certain amount of your memory is used for pointers and not data. So that's in principle seemingly wasteful. Arrays are nice and neat. What is a bad thing about, what other good things are there about arrays? Anyone else have anything good about arrays? What are bad things about arrays? Yes? Changing the size of an array seems like a problem, right? If you have to allocate a slab of memory, what is the size of a, you know, you have to allocate in principle, it seems, the size of the largest amount of memory you might possibly need, right? So if we're going to represent an array of all the students at Stony Brook, how big will Stony Brook be? Well, right now, you know, maybe it'll eventually be 100,000 people at Stony Brook, okay? You have to allocate an array as large as the potential number rather than how much stuff is actually in there. So that could be wasteful if you overestimate it. Because if you underestimate it, it looks like you're in trouble. What is good about a linked structure? In a good linked structure somehow, in principle, you don't need to worry about the size of the thing at the beginning. You're always saying, give me more memory as you need it, right? So in principle, your linked structure should be proportional to the size of what you actually have, not what you fear you might have. Does everybody agree with that? So if I think about what these things are, if I think about what is the big difference between contiguous structures and linked structures, In contiguous structures, there's sort of a trade-off between convenience, okay? Things are easier with one big slab of memory, versus the flexibility to use your memory more flexibly. That's what a dynamic structure lets you do. You use the memory for the data structure when you need it, okay? And that, I think, that's really where I see the big difference. Any questions? Okay. So let's move on. Let's now look at this a little bit more carefully. So with arrays, as we said, what are the advantages of arrays? We talked about constant time access. We talked about nothing being wasted. There's one other modern reason why some people like arrays. Okay? Computers now have caches. Cache memory. What is cache memory? You guys buy your computer. Okay? One of the things they'll tell you is how much cache is on the processor. What is that? That's some special fancy high-speed memory that is sitting between the real memory of the computer, sort of magically loading things in. And if you can work with data that's in the cache, okay, life is better, right? Everybody agree with that? Now suppose, let's say I give you, my data structure is a slab of memory, okay? If I am loading it into the cache in chunks, as I step through my array, I don't leave what's in the cache until I get to the end of that chunk. Does everybody agree with that? So there is sort of a coherence, a physical coherence typically. Since one of the things you do with arrays is go chomp from the beginning, 1, 2, 3, 4, 5. Okay? That's a good thing if you do that in memory, in an array. Suppose you have a linked list where the memory items, you don't know where they are. They're bouncing all around memory, right? What's going to happen as you walk down a linked list? Cache hit, cache fault, cache fault, cache fault, cache fault, cache fault, cache fault. Does everybody see that? So in principle, that's another advantage of arrays. Okay, sometimes it's an important thing. Okay, any questions? Big O-wise, it's not an important thing. Why is that? Cache memory may be 1,000 times faster than regular memory. What happens if we multiply our time complexity by a factor of 1,000? Does that change the big O-ness of it? No. So big O-wise, I'm not going to care about this. Okay? But sometimes it matters. Any questions? Now, the problem you were worried about with arrays had to do with the fact that you have to allocate the array all at once. Does everybody see that? Everybody grew up having programming with arrays. You have to allocate the whole array at once. The interesting thing is that that's not, you don't really have to, you can actually get not suffer from that problem if you're clever about how you use arrays. There is a fancy data structure that is probably implemented in some of your libraries called a dynamic array. Who's ever heard of a dynamic array? Who's never heard of a dynamic array? Okay, about half of you. So what is the idea? Instead of allocating an array of size as big as you need, let's allocate an array of a convenient size. Let's say 10 elements. Okay, 10 elements doesn't cost us very much, right? And now let's fill things into the array. Ka-chunk, ka-chunk, ka-chunk. Now I want to insert an 11th thing in my array. Now there's not room for it. How can I make the array bigger? Okay? Yeah? So in an ideal world, the best way to make it bigger is if no one had used that real estate yet, I could keep growing it. Right? Does everybody see that? The trouble is that's probably not true, right? The memory is being allocated. It's unlikely that once I got requested a slab, that the slab right after it is still there, right? What is the other idea? What if now I said, okay, you filled an array of size 10. What if I now allocate you an element, a slab of size 20? And I now have to start off by copying the first 10 elements in there. I now have an array of size 20. There's more room in it. It's now a slab. I have room for my next insertion. What is the problem here? What is the cost of doing this? I had to spend some time copying it, right? And now let's say you keep growing it. People keep registering for my class, ka-chunk. I now want to make it array twice as big. Maybe I'll make it a size 40, right? I have to copy all this stuff over. Does everybody see that? Question. With this kind of a scheme, is this an efficient scheme or a not very efficient scheme? Let's think about it. How many times might I recopy if I'm going to ultimately end up with n elements? How many times might I have to recopy? Okay. Someone with a hand. How many times might I have to recopy? Log n. Why is it log n? Because what does log n mean? Log n is how many times do I have to double something until I get to n. Does everybody agree with that? So when will I have something like n elements here? It will be about, okay, log n copies. You may say it's not exactly, why isn't it exactly log n in this particular case? Trivial reason. What is it? Yeah. No, that's not what I'm looking for. Yeah. Because I started, instead of starting from 1, I started from 10. Everybody see that? If I normally log n specifically is how many times do I have to double starting from 1, right? How many doublings will it be to get to n if I started from 10 instead of 1? Yeah? Log n minus log 10. That's right. It took log base 2 of 10 to get, if I was doubling from scratch, it would take me that many steps till I got up to 10, right? How many steps did it take to get up to 10? What is log base 2 of 10? Between 3 and 4, right? 3 and 4 is peanuts, right? So what's the real answer? In this case, it would be log n minus 3. That's why we have the big O, so we don't have to bother our mind worrying about things like that. Any questions? So with this scheme, what's interesting about it? The interesting scheme is we are never going to be doing more than log n copyings of any element. Which element gets copied the most? The first one is going to get copied log n times. Okay? What is the total amount of time it should take if I'm going to do n insertions under this scheme? Can anyone give me an idea as to how many steps it would take to fill an array from 1 to n using this scheme? Okay? The typical way that I would do it. Okay, what? Something like n times log n. That would seem to be my upper bound, right? How much total work am I doing? The element that is most busy is the first element. Does everybody agree with that? The first element is going to be copied n times. Log n times. Does everybody agree with that? I have n elements. Is any element going to be copied more than n times? No. Does everybody agree that n log n is an upper bound on the number of steps it has to take, right? The most expensive element is copied log n times, right? There are n elements. If each of them was copied as much as the most expensive one, the total time would be n log n. Does everybody see that? Who here does not see that? So I claim we have just proven that the dynamic time it will take for n insertions under dynamic arrays is big O of n log n. Does everybody agree with that? The interesting thing is it's actually faster than that. Okay? Although everything I said so far is true. Certainly one way to count the amount of work you have to do. If I want to figure out how much the average, let's say how much weight there is in this class, in terms of how many pounds people weigh. Does everybody agree I would get an upper bound on it by taking the heaviest person, their weight, and multiplying it by n, the number of people in the class? But isn't the actual weight of the people in the class might be a lot less, right? Suppose the class looked like this, here's this guy. The class looked like this, that would be a big upper bound, right? And what's interesting is for the dynamic arrays, this is a big upper bound. Let me convince you of this. If we think about it, here are the n elements. And this, if you're getting distracted here, I will let you get distracted. I think this is very cool. If we consider the n elements, how many times will the last n over 2 elements be moved? If we go do insert 1, 2, 3, 4, 5. Yes. They won't. Total amount of work for each one of these things is 0. Does everybody agree with that? Let's now picture we're using this dynamic memory scheme. We start from an empty array, and we keep inserting 1, 2, 3, 4, 5. How many total recopying steps are happening? We agree there's log n rounds of recopying. We agree that the first element here is going to be copied log n times, right? But most of the elements aren't. Isn't that right? The last n over 2 elements should never be recopied. Does everybody agree with that? Because somehow it's only when we doubled the size of the array. So these required no work. What about the previous n over 4 elements? How many times were they moved? Once. Does everybody agree with that? And that's n over 4 of them. There's n over 2 of them. How many elements were moved twice? N over 8. Does everybody agree with that? It's half each time. Does everybody agree with that? So I claim it's the following total number of steps that is done. In general, there are n over 2 to the I elements that are moving I times. Let's think about it. Actually, if you think, let's give this credit for 1 move, 2 move, we'll be generous. We'll overcharge it. Right? These n over 2 elements are each moving 1 time. That's 2 to the 1 is 2, right? These n over 4 elements, n over 2 to the 2, are moving 2 times, right? And we sum this up as I goes from 1 to log n. The important thing to see here is that the more expensive operation is being done by very, very few of them, right? What's the total number of steps? I claim this total number of steps is the actual number of copying times, which is going to be I. I goes from 1 to n. We pay I steps for each element that is copied I times, right? How many elements are copied I times? If you look at it, it's n over 2, n over 4, n over 8, n over 16. Do people see that it's something like n over 2 to the I? Does this make sense? What is n over 2 to the I as I goes from 1 to something? As I is 1, it's n over 2. As I is 2, what is n over 2 to the I? As I is 3, what is n over 2 to the I? You see that that's it. For these n over 8 elements, we're doing I, or 3 steps to do it. This formula counts the total number of operations we do. How many people see that? How many people don't see it and want to see it? Any questions? Okay? So what's interesting, if you simplify this formula, you factor out the n, that much you know how to do. You've got this I over 2 to the I. Okay? It turns out that this is a series that converges to n. Okay? This is a series that converges to a constant. Remember, what's the sum of I as it goes from 1 to infinity of 1 over 2 to the I? 1/2 plus 1/4 plus a third plus 1/8. What does that add up to? 1. Does everybody agree with that? Like with the Super Bowl coming up, the Colts get a penalty. They move halfway to the goal line. They move another halfway to the goal line. They move another halfway to the goal line. They're marching, keep getting penalties, moving halfway to the goal line. Do they ever score? The answer is no. Why? Because all those halves don't add up to be more than 1. Right? Does everybody agree with that? Same phenomena that we're seeing here. Okay? So the interesting thing is, in fact, on average, each element only moves twice. Big O of n log n analysis we did was an upper bound on the right answer, which by being clever we saw was in fact really theta of n. Any questions? So what's the moral of all this? First of all, dynamic arrays essentially don't cost any more than regular arrays, right? On average, they don't cost you any more. You don't have to allocate it in front. This shows you that occasionally, if you're clever, the basic analysis we did of what is the most expensive operation times how many times do we do that, that will sometimes give you an overestimate of how much time it takes to run. Do people see that? That's what happened here. The most expensive operation was log n. N times log n gave us an upper bound for running time. In fact, by being very clever, there was in fact a better bound, a tighter bound, and it was below the upper bound. Okay? Usually that's not going to happen in here. But I want you to see it and sort of be impressed with it while you see it here. Any questions about that? About the dynamic arrays and why they are a good thing? Any questions? Okay. Maybe I overdid this in here a little bit. So what is the other alternative to arrays? The other thing are linked structures. Okay? And linked structures, remember, are instead of allocating one big slab of memory, we're going to allocate lots of little pieces to connect by memory and connect them by pointers. So what is a pointer? A pointer represents the address of a location in memory. Okay? I think of a cell phone as a pointer to somebody, cell phone number. Why is this? I want to locate where somebody is. So long as I have their cell phone, right, number, I can call them and they will be, I can find them, right? The cell phone provides a way to get at where these people are, okay? And that's what a pointer is. With the cell phone, here's this person, okay? This person's carrying a cell phone, okay? If I have the cell phone number, I can contact this person, right? I can get access to them for anything I need. They have information, I can get it from them, right? What is potentially better about having a cell phone number of the information I need rather than actually having the information? Well, maybe the information is large, right? And so if I really need it, I can get it from the guy with the cell phone, right? By just calling him. All I need is the small cell phone number is the equivalent to get that information. The other thing is that if we have a pointer, lots of other people can also get that information. Does everybody agree with it? All you have to do is copy the cell phone number. And now lots of people have access to the same information. So those are the things that let pointers be good things. We don't have to actually have the information with us. We just have to know where it is to get it. Okay? and we can have many pointers point to the same thing, and that's a good thing. Any questions? Okay, so I'm going to use C in my examples of pointer programs, okay? Some of you may know C. Some of you may have grown, most of you I think grew up programming Java, and so the C may be a foreign thing. But if we're going to read it, when I say star P, if P is a pointer, star P denotes what is being pointed to. So if P is the cell phone number, star P is this guy, right? And of X denotes the pointer of this guy. So if this is X, and of X is the pointer to that thing. Okay? Any questions about notation in C? Okay? And the other thing that's sort of a unifying thing with pointers is this idea that there is a null pointer. A null pointer is a special pointer that we know means we've hit the end of the line. This is sort of a dummy pointer value. That when we do that, we know it doesn't refer to memory, but it refers to the fact that this is not pointing to memory. Any questions? Questions? So P is the same as star P. The answer is no. P is the pointer. Star P is the item that is pointed to by P. Okay? So a way to think about it is, suppose I have an item here. Let's say this item here is X. Okay? When we say and X, what is and X? It's a pointer to this thing, right? It tells me the address of this thing, right? Now, what is star of and X? What is pointed to by and X? X, right? So star of and X is the same as X. Does that make sense? Okay, good. Any questions? Okay, so let's look a little bit more about pointers. So here is an example of a linked list. Linked lists are made up of nodes. Our nodes are going to have two things in them. They're going to have a item type, a data item. That's what we want to store. It's also going to have a pointer to the next item in my list. Okay? This is sort of the data, and this is sort of the connecting. This is in some sense waste. These are the connections between the elements. This is the overhead I get for using a linked list, right? So in a linked list, what I have is a head pointer to my structure itself. It points to the first element of my list. Each element points to the next element until we get to the end. Nil or null, I probably use them interchangeably, means no more. That's the end of our list, and we know it's not there. Any questions? How do we search in a linked list? Okay. Now, many of you, if you saw a linked list, there's two different ways you can traverse a linked list. One of them is iteratively. What is the basic iteration you would use to search through a linked list? Yeah? While the next is not nil, meaning that I haven't bunked off the end of my list, is the element that's being pointed to by X, the one that I'm looking for, right? If it is, return it. If not, don't. Alternately, there is a recursive algorithm for searching a linked list. Look at this program here. Search a list L. L is, I now have a pointer to a list. If I'm looking for item X, if L is null, that means my list is empty. I can't find my item. If the item, what L points to, the data field it points to, is the value of X, return the pointer to it. Otherwise, start my search again from L.next. See how this is a recursive procedure? Lists are recursive objects because taking the head off of a list leaves a list. A lot of what's going to happen in data structures, many data structures are recursively defined. And they let us have these nice recursive procedures for it. Any questions? Okay. All this I can tell people feel dull. I know all about it, right? I like doing it. Okay. What's another example of something you might want to do with a linked list? Suppose we have a linked list here. And let's say that L points to that linked list. Suppose we want to insert another item into it. How would we go about logically inserting another item into it? So I have my new item, X. X, point to that. So L then points to that, right? Does everybody see that? I load up I allocate my item. I stick the value of the item I want to insert in the data field. I have it linked to the next item. And then at the head of the list, linked to my new cell. Any questions? Okay? So these basic list manipulation things, you did this in data structures. We're not going to really get into too much detail here about manipulating pointers. I'm sort of going to assume you know how to do that. Although most of the algorithms, we're not going to really be doing that much pointer twiddling. The important thing to realize, though, is that all of these data structures are concrete things. And when in a data structure, you say, oh, I'm going to delete this. You have to make sure you really can, let's say I'm going to delete this and it's only going to take constant time. The only reason it will take constant time is if in fact there is a program that does it. And so you have to think you have to really be thinking when you're working with data structures of the implementation that you're actually using to delete the item. Okay? Suppose, let's say you want to delete an item from a linked list. How do you go about deleting something from a linked list? Okay? What is the basic procedure? Somebody, yeah? You need a trailing pointer. If this is the item to delete, if I just have a pointer to the item to delete, what happens? Does that help me? Your answer is no. Why? Because for me to delete this item, I have to change the pointer in this node back there. Does everybody agree with that? And so basically this routine, again, I won't go through it. It's in the book and all that kind of stuff. To delete an item, you need to find a trailing pointer. Find the item to delete and splice it out, looking ahead. Any questions? What are the advantages of linked lists? Okay, linked lists, I'd say, are good things. We talked about some of the advantages. Okay, you can't overflow if you're allocating your list in chunks. You won't over allocate, you won't run out of memory until you really run out of memory. You just malloc a big slab, you will run out when that slab is full. Okay? Insertions and deletions are in some sense easier in linked lists than if we embed lists in an array. What happens if we have a bunch of elements, and I decide I want to insert a new element in an array here? If I have an array full of elements, empty spot here, but I want to, let's say I want to keep it in sorted order. I want to insert a new item here. In an array, how much does it cost me to insert that item? O of n. Why is that? What's expensive about doing an insertion into an array? Yeah? If I'm going to have to maintain the relative order, I have to shift all of these elements over, right? It might take n steps to shift the n elements over. If I know where I'm doing my insertion in a linked list, it takes constant time to link it in, right? So in some sense, it's simpler and more flexible with a linked list. Any questions? The other thing that, again, may get overlooked, but you should realize it. Sometimes when you are working with large data, it's easy to move pointers around rather than to move big records around. Let's say we're maintaining the database of your enrollment at Stony Brook. You have a lot of information about you. We know your name, we know your address, we know how many parking tickets and all of that kind of stuff you've accumulated, right? If I had to copy that information around in the data structure that they're using to maintain who's in my class, there is some overhead to copying that, right? What they're better off is just sticking in the data structure for Skeena's class is to have a pointer to your full record, right? And that whole record, I don't have to move around then, right? That's an advantage of pointers. Any questions? Bulky things don't have to be moved around as much. Any questions? Okay. So, once we understand why linked structures and contiguous structures, what their advantages and disadvantages are, we are going to be talking about various abstract operations in here that are going to be built from these components. The simplest, let's say, container of data that we have, let's go back there, is a stack or a queue. You all know what a stack is. We talked about it. Stacks have push and pop. Enters have, queues have insert, NQ and DQ. What is interesting about stacks and queues is that they support retrieval of data independent of the content, right? When you are looking at something in a stack and you say, get me something from the stack, you're not saying, get me the guy who lives in house 17. You're not saying, get me Skiena. You're saying, get me the last guy that was on the stack. Does everybody agree with that? So in case you are looking to retrieve elements without caring what the content of those elements are, stacks or queues are very good things. The difference between stacks and queues is the order that they retrieve items. Does everybody agree with that? Which do you want to model? A bank. Let's say you're at a bank and they're maintaining an order for how they're maintaining their line. Do they want, should they use a queue or a stack to maintain it? A queue. Why is a queue a good thing? First in, first out. Why is that a good thing? It's fair, okay? Does everybody see that? It's fair in the sense that anybody who came in after you isn't getting served until you're served. That's why it's fair. On average, the waiting time, if you used a stack or a queue, would it make any difference? Well, on average, it wouldn't make any difference. That's the interesting thing here. So a bank could say, hey, we're going to be just as efficient. We're going to use a stack. It will say your average waiting time is the same. You're happy, right? Okay? In principle, you're going to be unhappy. But recognize that it's not because on average you're suffering. It's because of envy that you're suffering. Any questions about that? Is the food in my refrigerator, or your refrigerator, if I had to take a guess, modeled as a stack or a queue? Okay? At least when I use my food in my refrigerator, I put food in, I put it in the front, right? I grab food. What do? I root for what's nearest to me, right? What is happening to the old food in my refrigerator? Probably don't want to know what's happening to that old food in the refrigerator. Does everybody agree with it? My refrigerator I maintain as a stack. Last in, first out. Okay? Other things, it makes a difference. Any questions? When we get to the reversal, you'll see that it makes a big difference which one you use. Okay? Sometimes it doesn't matter because the average case time for how long items are waiting doesn't matter. Sometimes it does. I don't want to go through it now. But sometimes it does. Any questions? The other abstract data type that is probably the most important abstract data type that we will talk about is the abstract type dictionary. A dictionary is what would also be a dynamic set. Again, when we think about abstract types, an abstract type is defined by what operations the type performs, right? So a dictionary operation is going to maintain items where we're supporting retrieval by content. You want to be able to insert Skiena. You want to be able to retrieve Skiena. Not the last guy you inserted, but you want to retrieve someone in particular. I want to carefully review what are the 6 elementary operations that we will assume a dictionary data structure supports. Okay, because it's important to get the precise definitions of these things right to understand what we're going to be doing. In a search operation takes 2 arguments. It takes as input a dictionary data structure, that's S, and it takes a key, Skiena, okay? And it asks us, is Skiena in the key of one of the elements in that data structure? If it doesn't, tell us it's not there. If it is, return a pointer to the element such that that element is there. The pointer of the element associated with that key. Question about what search is doing. Now, insert S says that you were given an item X, a pointer to an item that contains a key and possibly some other data element, and a data structure. And it says insert the difference. Insert that element into the data structure. Any questions? Is it sorted? That's a question of details. How is it done? Inserting it means you have been added. If we have a set, if our dictionary is maintaining the people in this class, you were inserted into this class when I signed an add form, right? Whether it's sorted or not is an implementation detail at this point, right? It's a class. What's a class? It's a black box of students, okay? So that we don't know. We may choose to implement it as a sorted array. We may choose to implement it as an unsorted array. We may choose to implement it as a sorted linked list. We may choose to implement it as an unsorted linked list. These are implementation details. And they're not details in the sense that they will affect how fast these operations are. Okay? But for now, that's a black box. When we talk about here, what the operations are. Any questions? What is the difference in the arguments here? This is the subtlety between search and insert. What is the difference in the arguments? One is K, one is X. One is a key, that is Skiena. One of them is a pointer to a record containing the key, that is Skiena and his life records, where I live, my parking tickets, whatever else they have about that. Any questions about that? So there's a difference between a key and a pointer to a record. Okay, the key is used for search. Any questions? It's going to make a difference later. Delete. What does delete do? Given as input a pointer to a record, a pointer to the element in the set. Given the data structure and a pointer to the record in that data structure. Delete removes it. How would we get that pointer? Everybody see the argument here is an X. How could we get the element if we're using a dictionary, an abstract dictionary? The way that we can get the pointer to the element to delete is by doing search. Does everybody agree with that? So when we say, can you delete Skiena from this class? Skiena as a key, the answer is no. If you want to delete Skiena from the class, how would you do it? You would call search, saying search for key Skiena. Return me a pointer to the item to Skiena's record. Delete is expecting as an argument a pointer to it. Okay. Any questions? Any questions about why we might want to define delete in terms of the pointer to the item instead of the key? What's useful about that? Yeah. Okay. What if we have a pointer to it? It might be expensive to find the pointer to it, right? If we define delete in terms of a key, we can always implement it by doing a search plus a delete of a pointer element, right? But if we happen to have the pointer, it might be expensive to do the search relative to the actual snipping of the item out. Does everybody see that? So for efficiency, it pays to decouple these operations, because we can get the effect of key deletion by always doing a search and then a delete. Any questions? Okay. What are the other operations that we're going to support? Min and max return either the smallest or largest key in alphabetical order. So what would the min of the people in this class be? If I have a dictionary representing the people in the class, who is going to be the min? Not the first one to register. That was the first one inserted. We're not retrieving them by order. We're retrieving them by key value. By min, what it would be is the person in here whose name is AAA Finster. Okay? The one first in alphabetical order. And who is the max? It is the one with the largest key. Go back there. Oops. Go back there. Who is the max? That's the one with the largest key. You'll see how we're defining these operations? Any questions about that? So max in this class would be Zygmunt. Okay, I don't know if I got any student named ZZYQVMB. I can get spam from people like that, actually. Right? So that would be the max. Okay? This is defined in key space, not in order space, because we're dealing with an abstract operation on keys. Any questions? What do the next and previous operations do? Let's read that. It says that next of x is going to return us, given a pointer to an element in the data structure. It is going to return us the next element, the next largest element in sorted order. So suppose we have a data structure which has the following people in it. Mary, Bill, Joe. Given a pointer to Joe. Well, let's say somebody else. Let's insert William. What is the next element after Joe? Well, it's the next one in sorted order. It would be Mary. Does everybody see that? So next and previous operations, we're given a pointer to the item in the data structure. And we want to quickly find out who's next in sorted order. Okay? Previous is who's previous in sorted order. Okay? Any questions about what these operations are? Look carefully at what these operations are, because your next problem of the day is going to be asking you to implement a dictionary. Describe how you implement a dictionary using sorted and unsorted linked lists. Okay? For all 6 of these operations. This is very important that you work out the next one carefully to understand data structures. Okay? So definitely do the problem of the day. Try to do it seriously. Okay? And we'll talk about it next week. Any questions? Thanks for your attention. See you then.